Hi guys, my name is Hari and this is Project Directory, where we'll be focusing on technical videos related to projects that I and the OSS community have built. So it's been a while since my last video and I have been keeping myself busy with college. But today we are attempting something that I've been working on for a while at college that might also be slightly controversial. We are going to try and fix the C programming language. Before we dive into today's project, recently I've been interested on how a programming language is created. Let's talk about how compilers actually work. We often think of them as black boxes that turn code into binaries, but under the hood they are complex pipelines. A compiler first reads your text, which is called lexing, understands its structure, which is parsing, and then crucially analyzes its meaning, that is, semantic analysis or the grammar check in simpler words. This third step, semantic analysis, is where Rust truly separates itself from the pack. While most compilers just check if you missed a semicolon or used the wrong type, the Rust compiler runs its famous borrow checker here. It uses this phase to prove your code is memory safe before it ever lets you run it. If you watched my previous videos, by now you know that I love Rust. I love the safety guarantees, the borrow checker, the way it stops me from shooting myself in the foot. But the reality is, the world runs on C. The Linux kernel, Git, Python's interpreter, and your toaster, it's all C. And C is dangerous. It lets you manage your own memory, which means it lets you also mismanage your own memory. Double freeze, use after freeze, uninitialized memory usage, these are the bugs that cause 70% of security vulnerabilities in your major software. So then came the thought, what if we could take the brain of Rust, that is the static analysis and the ownership tracking, and apply it to C? What if we could write a tool that reads C code but judges it with Rust's strict standards? Enter COW, a borrow checker for C written in Rust. This isn't a rewrite, it's a static analysis tool that parses your C code and yells at you if you violate ownership rules that C doesn't even natively have. We are enforcing Rust's discipline on C's chaos. So, let's build it. Since I've already built it, here's the plan for this 15-minute speed run. First, we'll talk about the architecture. How do we even read C code? We'll talk about lexers and parsers. Next, we'll talk about the abstract syntax tree and how Rust's enums make representing language syntax incredibly easy. And then we'll look at the brain, which is implementing the symbol table and the ownership logic. This is where the actual magic happens. And lastly, we'll run the demo. We'll run it against some valid C code, valid in quotes, that is actually a pretty big memory safety nightmare. To analyze code, we first need to understand it. We can't just reject our way through a C file, that's just madness. We need to build a proper parser. I didn't know about this before I started this project, but the way I go about doing this, apparently, is by building something called a custom recursive top-down parser. Here sometimes also known as a recursive descent parser. It starts with a lexer. What the lexer essentially does is that it takes a stream of raw text characters and chops them up into meaningful chunks called tokens. If you take a look at lexer.rs, you'll see that it's just a state machine. It eats up white space and identifies keywords like int or return and bundles everything else into identifiers, either identifiers or literals. Once we have tokens, we feed them into the parser. The parser turns a flat list of tokens into a hierarchical structure called an abstract syntax tree, or AST. This is where Rust really shines. An abstract syntax tree, or AST, is a tree-like representation of the source code structure. So think of the AST as the skeleton of your code. It takes that flat list of tokens and organizes them into a tree-like structure that actually shows how the code fits together. In Java or C++, an AST node might be a base class with a dozen of subclasses. In Rust, we just use enums. Look how clean this data modeling is in ast.rs. A statement here can be a return or an if or a variable declaration. We don't need null checks or dynamic casts, we just pattern match. The if variant holds the condition, which is an expression, the then branch, a statement, and optionally an else branch. You can also notice the box around the statement, which is just a pointer to a statement, since statement is recursive. An if statement can contain other if statements inside it. So we have to box it so that the compiler knows the memory size. This structure allows us to represent the entire C program as a tree of data that we can traverse. Now that we have the tree, we need to traverse it and look for crimes. This logic lives in mod.rs. We need to track the state of every variable. So in C, a variable is just bytes. But in our borrow checker, each variable needs to have a state. I've defined this state in scope.rs. This is the core of the project. The parser should now recognize these states of variables. Starting with uninitialized, which means you declared int x but gave it no value. Reading this is a bug. Owned, meaning you have the data and you are responsible for it. Moved, in a sense, you gave the data to someone else. You can no longer use it. Dropped means the scope ended and the variable is gone. Now about the symbol table. A symbol table is basically the compiler's address book. It's where it writes down every variable name you invent and keeps tabs on them. So whatever variable we create, we track its state across scopes. When you enter a opening flower brackets block in C, you enter a new scope. When you hit closing flower brackets, that scope dies. I implemented a symbol table struct that essentially manages a stack of hash maps. Think of it like a stack of transparent papers. Every time you enter a new block of code, which is a new scope, we put a fresh sheet of paper on top. When we enter scope, we push a new hash map onto our stack. When we declare a variable, we write it on that top sheet. When we look up a variable, we look at the top sheet first. If it's not there, we peek through to the sheet below it. This is exactly how shadowing works. A variable on the newer sheet hides one with the same name on an older sheet. Now comes the controversial part. C doesn't have ownership. So if I do int x equals 10, int y equals x, and return x, in C, this is valid. X is copied to y. Both exist. But co enforces move semantics. We are essentially pretending C is Rust to catch logic errors. In mod.rs, look at how we handle assignment. If you assign x to y, our analyzer marks x as moved. If you try to use x afterwards, the analyzer sees variable state moved and throws an error. So we basically have implemented a use after move checker for a language that doesn't strictly support moves. Why? Because if x was a pointer to mallocked memory and you copied that pointer to y and then both x and y freed that memory, you have a double free vulnerability. By enforcing moves, we prevent multiple variables from thinking they own the same resource. So finally, let's see it in action. I have a simple CLI built with clap in main.rs. It takes a file, parses it, and runs the analyzer. Let's take a look at testownership.c. If I compile this with GCC, it's fine, it runs. But let's run it through co. Yes, it got it. We assigned x to y, so x is moved. The return statement tries to read x, and co says absolutely not. Let's try another one. Uninitialized memory. The analyzer checks the symbol table for x. It finds it, but the state is variable state uninitialized. Boom. Error. You might ask, Hari, isn't this overkill? C integers copy by default. They don't even move. Yeah, for integers, it is overkill. But think about pointers. Think about file handles. Think about sockets. In large C code bases, passing a pointer around without knowing who owns it, that is, who is responsible for freeing it, is the number one cause of leaks and crashes. By forcing a programmer to be explicit, or by at least visualizing where ownership is transferred, we can catch logic bugs before they become security patches. Currently, core is in its early stages. It treats everything as a move, which is aggressive. A future version would differentiate between copy types like int and move types like pointers, or strings for that matter, similar to how Rust does it. So, what did we learn? Building a compiler frontend isn't black magic, it's actually just data structures. We used enums to represent the syntax tree, hash maps to represent scope, pattern matching to traverse the tree and apply the rules. This might honestly be the most fun I've ever had while writing code, and Rust made this tooling incredibly easy to write. The entire project, Lexer, Parser, Analyzer, the CLI, is less than 1000 lines of code. And that's crazy. If you're interested in compilers, don't start by trying to build LLVM. Start by building a linter. Start by building a syntax highlighter. Start by building core. The source code for core, initially called Borcom, is available in the description. Clone it, break it, add support for pointers, etc. and let me know how it goes. Thank you for watching and stay curious.